So that's the menu for, let's say that will be the menu for, well, one thing before we start, I put an announcement on Blackboard because the delivery of the exercise, we are going to do that through Inspera, not through Blackboard. Because they want to test the system that's supposed to be for all activities that account for the grade. Okay, so they want to do it through Inspera. And they were asking, because they have to set up the system beforehand, so they were asking if you will keep always the groups will consist of the same members, or if you plan to change the group along the semester. So I have put a poll in on using Google Forms, but I maybe want to ask you, if do you plan to stick to the same group, or do you want to have the option to change in the future? Hmm? How many want to will keep the same group? How many will change? Will think that maybe you will probably change group in the future? You won't be a trader, but maybe that you want to try something new, or you want to try with different nationality, different, no? Nobody? Okay, so I'm going to tell her that depending on also on the results of the poll, that we want to keep the same group for all the assignments. Okay. Okay, so now going back to the technical part, we're going to continue. I hope you remember this class example we're working on. That basically we want to estimate using Monte Carlo the distribution of n, okay, which is the initial oil in place. And we are using the input of petrophysicist A. Then we are going to look at those results and the way it is usually presented. Okay, we will see, we use the probability distribution that we find, but we also calculate the cumulative, and we compute some values that you will see very familiar in the reserve estimation part of the PDO, P90, P50, and P10. By the way, have you heard about this nomenclature before? Yes? No? How many of you have heard of it before? 1, 2, 3, 8. And you're not from petroleum, so... Well, you're not from petroleum, and also you're not from... So where did you hear from it? Like, out of Juan Manuel?
Yeah. From my bachelor's.
Bachelor? Okay. Okay, but not related to reserves. You just heard of the term P90, but not related to reserves. Okay. Some more things that I forgot to say last class about Excel. Some more tricks and considerations that might help you. Then I'm going to give the formula for the triangular distribution. That's something you need. Okay, all the exercise we are doing here is with uniform. So we want to use, you have, two variables that you want to use triangular, which is the porosity and the recovery factor, right? And then finally we got to the main question. They say, well, how do I estimate this number of iterations? And instead of giving you the formula, I want to give you like the background. What is the justification for that formula? Okay, but let's see if I'm successful or not. Okay, and then hopefully let's see how, depending on how much we cover, but go to another topic completely different, to say the layout of production systems. Okay, that's going to be like something we need for jumping into the offshore structure part. Okay, so let's see the example we were doing last class, if you remember. Let's see if I also remember. Okay, so we said we had all of these, let's change to hand. Okay, so we have all of these which we had to multiply, then we had to divide by BO, and that will give me n, right? So then I say, well, all of them are uniform. Okay, yeah, I remember now. Sorry, one more thing we have to cover is okay, something that you will need for the example is, for the homework, is a conversion between discrete to continuous distribution. Okay, sorry for the detour. So we were saying, well, we multiply that times that times that times that. We divide by the BO, and that's the formula of n, right? And then we said, well, this is uniform, and we really could take either a random value between 5 and 6.5, okay, any random value, or the proper way to do it and the consistent way to do it is that you go to the, if you remember, we have the PDF, okay, which might look like that, but we actually are going to sample on the cumulative distribution function, cumulative probability function, okay? The one that tells me if I integrate that number from here to here tells you the cumulative probability of that value. And then we say, well, what is so convenient of doing it like that? Because it's actually bounded, the function. Goes from 0, cumulative probability, to 1. And then you can use a random number between 0 and 1, for example, 0.5, and you go and you read the number that you have. Okay, without, depending on the range, is completely general. So that's the philosophy, and that's the thinking behind using this, the cumulative probability function, okay, the CPF. And I told you, well, for a uniform, that's the formula you have to use, and actually that's the formula we programmed in each one of these lines. Okay? So then I told you, well, that was some sort of a problem. The guys with Mac, did you solve your problem? Yes?
It's not comma, semicolon.
Semicolon? Okay. Yes. So let's also see some comment before we say, okay, let's say here mention some tricks. So in, I think it's in every, or in Windows at least, maybe in Mac also, be careful that in the newest file format of Excel, actually you find two options, okay? One is called .xlsx, okay? And that format you have to use only if you have no macros, no functions, no VBA, anything. Here it's say must use only for spreadsheet info, okay? Doesn't, so be careful, doesn't save any macros, okay, or any VBA information. Be careful, because if you, let's say you're working 3 days without saving on your Excel sheet, and then you click save and you go to sleep, you wake up, you open the sheet again, it's going to be empty. You lost the whole 3 days you've been working on. Okay, so if you want to save the macro, you have to save with a format called XSLM, okay, which is like macro enabled Excel sheet. And I think it's the same for Mac. Okay, you have the same. So be careful if you have to have any macros, anything you want to say with the newest file format, you have to use XSLM. Okay, macro enabled workbook. It's called macro. Otherwise, you're going to lose everything. So be careful. Macro enabled workbook. If you're using, the old format, okay, the old format is just .xls. So yeah, .excel. If you're using that format is called 1997, 2003, then it doesn't make a distinction between the two. Okay, you save in that format and it contains both spreadsheet and VBA, okay, or macro. So some files that are going to give you, even though they don't have that extension, they are annulled from an old version of Excel. Okay. So you decide what you want to work with. I can open both, but be careful if you want to save a macro, use that format. Okay, that's very, very important. Also, what our friends, Mac friends here are saying is that some functions you have to split in some computers, the separator for the function variables is not comma, okay, is semicolon. Okay, for example, you have a function which is multiply. Okay, you take A, B, and C, and then you say multiply is just A times B times C, right? And then you say end function. When you want to call that function, okay, let's say you have an A here, which is 1, B, 2, and C, which is 3. When you want to call here that function multiply, some computers you will have to use A, comma B, comma C. Some other computers you will have to use or A semicolon B semicolon C. Is that the problem you had? Yeah? Okay. So be careful. I had that written here, but okay. And another source of error is that be careful that so let's click this Alt F11. That if you write any function in the module has to be below the main Excel sheet that you're using. Okay, if you can type, maybe sometimes you create a module out here and then the Excel sheet won't see it, okay, because it's located outside. You might here have 7 Excel sheets open. So when you create a VBA function and you want to use it in this particular sheet, be sure it's in this module. Has to be saved in this module. So let's put a small comment on that. Okay, so be careful if you want to use it here, this particular sheet. I know that, you know, all of you are smart, but maybe you have a bug that doesn't read, doesn't find the function. You ask the assistant, you ask me, you ask your friends. It's a big trouble, and then was, you know, just a simple thing. Okay. Yes. So now let's go back to the exercise and let's analyze the results. Okay, we have all of that long column, right? So now we have to create this probability distribution function, right? That's what we want to create. And the way we are going to do it, I suggest, so let's take that particular column, okay? If I want to select the whole column, I go Control, Shift, and down, okay? And then the selector takes all the way from the cell where I am all the way to the last one, okay? Control, Shift, and down. I copy, Control C, and I'm going to use another sheet to process the results. I'm going to call it here Postprocessing. Okay, and let's paste it here, and be careful, I don't want to paste the formula, but I want to paste just the values. So I go here, paste values, and this one, 1, 2, 3. And to know exactly what it is, well, I'm going to take just the header from before and paste it here. I don't want to make it here because remember, any change I make on this sheet, okay, I click put one. Remember, I have this random function, that is changing automatically all the time. So I want, after it calculates once with one set of random values, I want to analyze those results. I don't want those results to be changing all the time. Okay? So that's why I'm using a different post-processing, and we say this will be the post-processing for N, right? And petrophysicist A. Okay, the results of N for the petrophysicist A. So the first thing I have to find, remember the range, right? I have to find, to make we are now doing the PDF of N, right? That will be something like this, where I have the probability of a particular N. So I need first, I will say, calculate the N minimum and the N maximum, right? To see the extent of my range. So for that, any suggestions? Min N, right? And that will be we're working in just standard barrels, which is a very big unit, not very comfortable to work with. And max N. Those of you who are experts in Excel, what do we use to find maximum and min?
Max min function.
Okay, max min function, very well. So we say just call it like that, min, open parentheses, and we have to give the whole range, right? So control district, control shift down, close parentheses, and enter. And we should put that, let's say, let's change the format of that number to scientific. Okay, 168 million. That's the minimum initial oil in place that we have from our Monte Carlo simulation. Is that a big number or a small number? What is big or what is small? But that's like the size, more or less a bit smaller than the size of Goliath. Okay, so it's like a medium to small size oil reservoir, more or less. So maximum, we can copy the same. Is some of you solving it with me, or you're just watching? You're just QC. You're doing okay. You are the managers. I'm the engineer giving the results. Okay, 500 million barrels. Okay, that's the range. Now what I have to make, I have to decide, okay, how many I myself, okay, arbitrarily, I have to decide how many slots I want to make in this diagram. Okay, I have to, this one was 168, was it, million, and 534. Right? So now I have to decide what I'm going to put in between. Okay, how many values I'm going to put. That's something that you will decide. I leave it completely to you. But here, maybe we can use, I don't know, 15, you think? 15 points? You will see now why we need to decide these points. Okay, but let's see, we want 15. From here, that will be 1, 2, 3, all the way to 15. Okay, 15, let's say, numbers between 168 and 534 that I'm going to use for something, that I'm going to put here in each one tick of the x-axis. So how do I do that in an automated way? So I will say here, create one more column, N standard barrel, and that N will go from the mean, right? So here I have to put the mean, and I have to go to the max, right? But I have to populate all the values in between automatically. So any suggestions how to do it?
Add difference divided by 15.
Yeah, so what engineer here, the support engineer I have, is suggesting that I should use the n of I, right, is equal to n mean plus n max minus n mean divided by the number of points I have. Is it 15? So let's put n points times I. Yes? And I goes from 0, right, to 15. That correct? Okay, so let's see if it works. Okay, so let's put that formula here.
If we want like 15 points, then it goes from 0 to 14.
Exactly. Okay. Well, let's try it first, and then we check if the second support engineer I have is correct. If you're not sure, you try. Okay. If it doesn't work, then you something wrong with your formula. Okay. So let's see. That will be minimum, right? Plus. But we need a counter, right? We need an I. So I'm going to make it a bit easier. I'm going to say this is the same as saying this one, the previous, plus the difference between this number, and I have to lock it, remember, F4 minus this number, F4, divided by 15. Yes? Everyone agrees? So in a way, when I drag it down, it will take the previous number, and it will just increase incrementally by this factor, n max minus n min divided by the number of points I want. Okay, so let's see if it works. Okay, 534, and how many points I have?
16.
Okay. Here it says if you select the whole column, here you see it tells you below count is 16. Okay, so he was right. Why is that? We are making 15 subdivisions, right? But we have at the end 16 points. Yes? Clear? Or not too much? Clear? Okay. So here, actually it was, in this formula, 216. Because we have 15 spaces in between. Here we say 16. Okay, and we have to go from 0 to. Okay, after we have that, now we have to go and hire, you know, maybe your sister, your brother, someone that, you know, needs money and is willing to do everything, anything, you know, no matter what. And we have to say, now you have to come to this list, 1,000 values, and you have to tell me how many times 168 comes up. And that's really a very ungrateful job, okay? To go through the whole list and say, well, how many times I have. But you will see, you won't find exactly this number, right? Remember, this number has a bunch of decimal points. So probably that number happens only once, okay? So then he thinks he's smart, okay, your little brother. He says, 1. I'm going to put 1 in all of them. The thing is that the way to do it is, I will say, I want to count all of those that are between 168 and 192, are around that number. And I define that number. Excel has a way to define that number. But I'm going to say you have to count the number of occurrences, okay, in n. So this will be in the column n of 100, if this is 168, right, of the range between 168 and, I will say, half the interval. That's something I define completely arbitrarily, okay? But I will say 168, what's the next one? 192, right? So yes, everything that is within this range, you're going to count it and put it inside the bin of 168. That means that any number, okay, that is in this range, exactly in the center, and that's something I define completely arbitrarily, you're going to count it and you're going to plot it and put it in this number. Okay, for 192, you're going to take. So what are you going to take? Let's see if you 192. It will be between 192 minus 192 minus 168 divided by 2, all the way to 192 plus the next one on the list, right? Which is 216. Okay, clear or not? So really I'm not looking exactly, the point here is that I'm not looking exactly for these numbers on the list, because maybe they will appear once, maybe not. I'm looking for all those numbers that are in a range around that number, around 168. And that range I define arbitrarily. I could say, well, the range will be in the center, the range will be from here below, for example, will be, this will be the range. I define arbitrarily how that range is. Okay, but in this case I'm saying, well, it's half. Between this and the next one is half. That's where the boundary is. Okay. Now to make that process automatically, we don't have to use our little brother, okay? Because if you have to run 8,000 iterations, 10,000 iterations, you will have to pay, a lot of money. So we are going to use a function called frequency that Excel has. So here we say the count. Okay, we're going to create another column called count. And here is where I'm going to apply that frequency function. Frequency is like my little brother that is going to come and count all of these occurrences according to these predefined values. Okay, I give the list of predefined values and I say count here. Okay, but that function is a function that gives you back all these values at the same time. So it's not a scalar function, it's a vector function. Okay, like the functions that we have seen, for example, here before, this multiply. This function takes 3 inputs but gives you only 1 result. So it's a scalar function. But this function, this special, it has to give me the number of counts for each value. So it's like a matrix function. Okay, it's like a vectorial function. Yes. Okay. So now we say, so the step for doing that, we select the whole column. We say equal to frequency, and that's the function I want. First I have to give the data, the raw data array. Okay, it will be here. And remember, I use again this trick, Control Shift down. Then I use comma or semicolon. And then I have to use the bins. What they say, the bins are the predefined values I want to look for in this whole population. So this will be these guys. Okay. Close parentheses. Then to apply this function, it's not enough to click enter, but it's a matrix function. You have to use Control Shift enter. Control Shift enter. Okay, and that's the way you apply. You have to select a matrix function or a vectorial function. You have to select the whole range. Then you have to write the expression, and then to apply the expression, to click enter, you have to click Control Shift enter. Okay, so I'm going to put a small comment on that so you will remember when doing the exercise. So frequency is a vectorial function select the output range okay, then you have to write the formula on the formula window, okay, and then you have to provide input, and then to apply the formula by pressing sequentially, you can do it sequentially, Control Shift plus Enter. Okay. Now we can do a one quality check, which is the sum of all of these numbers should give you 1000. Okay, because it assigned that number 243, for example, assign it maybe here to 241. So it should be the total number that I have here should be also the total count that I have here, which is 1000. So that's fine. Okay, that looks very correct. Then I want to calculate. Now I calculate the relative frequency, which is the count of that particular bean divided by the total number of points. So that will be relative frequency, or we can already call it probability, right? And I'm saying that will be this number divided by, okay, the total number of points, which was 1000. Okay, I can put it like that. Okay, and now let's let's plot it, because we should get exactly that shape that we expected. And to plot it, we have to use a bar chart, 2D column. Okay, and let's select the data. Okay, on the name you have to put these numbers, I think. No, on the name you leave it, you just put n, and on the series you put those numbers. And here, the horizontal axis, you have to select the values of n. Okay, so once more, add. Here you have the name of the series, which is just the initial oil in place, or n. Here you select the relative frequency, or the probability that you just calculated. And on this side, you find what will be the tag, okay, that you're going to use. And we're going to move that. Like I told you, I don't like to have plots next to the data, so I'm going to move that plot to a separate place. That will be n distribution of n, right? Now this is not up to standard, so let's increase a bit. First we increase the font size. Let's see, 16. Doesn't cry. Let's put it in black. We want also in this plot we want to put axis title, and that will be in fraction, the probability. That will be initial oil in place and standard barrels. And then I want maybe to put the y-axis, right? And I want to put something important that is also helps to read the number. You have to use the tick marks on the outside, and also here it helps if you put the tick mark outside. Okay, maybe I want to make it a bit darker. And then I can take maybe that one away. And now the only thing, you see it has a shape that we more or less expected, okay, more like a normal distribution. But to make it a bit nicer, remember that this number applies not only for this particular number, but actually for the whole interval. Okay, so we have to reduce the gap between them. So that you do by maybe clicking here, gap width, and I drive it all the way to 0. Okay, and then everything looks blue, so I want to put the lines also. Okay, you will have all of that solid line in black, and that looks much nicer. So that's what I obtained with my Monte Carlo. Not only, and the power of that is that you don't only obtain one value, okay, or sensitivity in a very simple way. You said, well, if this is maximum and all of them are constant, what will be my initial oil in place? This graph is already taking into account all possible variations, all possible combinations of this universe of values. And it's telling me, for these 1,000 iterations that you made, this is the most likely, or that's the average value that you are going to obtain from your field, which is 300 million barrels. Okay, so let me copy that. Okay, any question before we take a break? Yes?
Is the bin interval from, for example, for the first one, it's 1.68 to 1.92, or it's 1.68 to the midpoint of 1.68 and 1.92?
The interval is from here, that's 168, right?
So
to here. The middle point between this and this one. So that's how the bins are being counted. Yep. But okay, I tell you, that's what I tell you here, but you have to go to the web and find what exactly this frequency function is doing. Okay. Yeah. But let's take a break, 15 minutes. Is there any other question? No? Let's take a break, and we continue to see how, some other comments on this result.
I think I did something funny because I just get one.
That's what, because your formula is not frequency.
No, it's the one next to it.
Oh, here.
Yeah.
Okay. So you can just, I think sometimes the easiest way is just delete the whole thing. So where do you delete? Yeah. Okay, so now try it again. Equal. Frequency. Now you select from here. Control, Shift, down. Oh, that's a Mac. So A4 will be to A. 1004, comma, and here you
No,
have
it's the other one, no the comma.
the semicolon. And then you have to have this one. Okay, maybe the command in Mac is different. So Control Shift.
That one worked, I think.
Yeah, you're getting some.
Strange numbers.
Yeah, it should be centered someplace here. So go check maybe. Do you have values all the way to 1004?
Yes, because that's what I got from. Well, 1003.
Okay, so
Maybe
maybe
that's-
that's part of the reason. So if you want to edit the function, you have to select the whole thing, and then click here, 3, and then it doesn't gives you the same. So you see you have 957 values. So I don't know why.
Can we use the data analyzer tool to get the histogram? It's the same thing,
You can
right?
you can use this. Yeah.
Because I couldn't do it this way, so I had to use data analyzer.
1003. So why?
We did minimum, maximum, something wrong. No, in this one.
Okay, the previous, and you're just dragging that function up, and here minimum. No, I'm not sure. And those are the results you got from here.
Yeah. I copied this one. Is this one right? And
Yeah, it's this column. Yes, so maybe there is something wrong here. C5. D5. Could you just copy that and take it again? Maybe there is something.
I think you can use the same no control function
Down.
down.
Okay.
I think when no, it doesn't. Okay.
I'm not sure how, because this trick should be working with
Command shift. It's command shift down.
command
Command shift and down.
command shift down. Okay. Values. See, but the minimum is not 293. You have here one which is 226. Oh, yeah, here that's the problem.
2
Because
points.
now you were giving the minimum. Now it gives you something different. So this one should use the minimum. These two. And now it changed. Now looks a bit better.
Much better. Yeah. Okay. Thank you very much.
Can you
Just wait, let me
use
just pause here. Okay, so that's we found exactly what we were hoping for. This plot, not what you need with unique value, but actually we get a range of value, and each one with an associated probability. And here you see that's from a PDO I didn't give to you, but it's also available, I think, on the web. So that's a field Karish and Tanin, and they show it's a field of gas. Okay, gas gas initially in place, and you have again the same what they report. But one nomenclature which is typically used, you provide, now most PDOs they provide you with that figure, but they provide also on top of it the most common value is to give the P90. Okay, these are what is called the proven, okay, proven reserves.
Sorry,
Yes,
you record the
I think so. No, yeah, okay. Okay, proven reserves is those reserves, that number, that I'm sure I have at least that number or more than that. 90% chance that I have that number or more than that. So let's see, I usually have a lot of problems making sentences when teaching. So let's see, it's the quantity for which there is a 90% probability that the actual reserves are equal or higher. Okay, so that's the number, and those are called, nomenclature. Normally you use the term proven reserves. And that P90, that's something that we use in Norway and in many other countries. But in principle, that number can change any place from 100 to 66%. So what would be P100? The minimum, okay? You have all the other values here are greater than 168, all others. So P100, you are 100% sure that you have at least 168, not less than that. Okay? And then you start increasing. Okay, here, you'll see how we do that in a moment. But keep that in mind, that range is a range actually, okay? You can change it from 100 to 66. And 66, that, is it more conservative or more, or less conservative? Less conservative. Okay, if I reduce that number 66, I become less conservative. And some governments accept, some accept a lower value. P50, those are the proven plus the probable reserves. So it's again the quantity for which that should be which, right? There is 50% probability that the actual reserves are equal or higher. And then I have, and that P50 can go all the way from 66, if you're very conservative, all the way to 33%. And then I have P10, and that's called proven plus probable plus possible. Okay, and again, let me just see if this works. The quantity for which there is 10% probability that the actual reserves equal or higher. And those are the three numbers we normally use. If you don't want to give the distribution, that's fine, but those are the three numbers you have to give every PDO. Okay, and we can do it in terms of the initial oil in place. You can give the P90 of the N, but you can also give P90 of TRR. That's also something you will have to do in this exercise. And they have slightly also different names in you know, depending on the country, the company. So they try to prove they use secured reserves. They use all kind of strange names, but basically that's what it means. And to find those numbers, actually we have to compute to obtain these numbers. We have to compute the cumulative probability function from the probability distribution function. We have to say that it looks like it should look something like this, okay, between 0 and 1, and we have, remember, this axis goes from the minimum, sorry, this is N, right, in standard barrels, and it goes from N min all the way to N max. We can put actually N min all the way here. Okay, and how should it look like, this curve? Okay, like an S shape, and going here is the open part, and here it starts to go down. Okay, because if you want this P90, so you go 0.9 and you read the number here. If you want 0.5 P50, that will be P90, P50, and P10. Okay, so let's create that from the data we have, just so you'll have it on your notes. So how do we calculate the C cumulative probability distribution, CPD, or function? So how do we calculate exactly that we get that shape? We have to go from bottom up, right? So the cumulative here will be just this one, because I have nothing else bigger, right? But on this one it will be, sorry, on this one it will be the current plus the previous. Okay, and then I increase and go up. Okay, and that should give me 1 for N minimum, and that should give me close to 0, almost nothing for N max. That clear? Yep. Okay, so let's plot that, which was thing we have missing. Okay, for those of you who were asking to put it on a new sheet, you have to click here on the white part, such that all the corners are, you know, you have a circle, and then you right click, move chart, and here I will say cumulative distribution, probability distribution for N. Okay, and now I have to fix some things. Okay, I forgot to select the y-axis. So that will be here. Okay, and the maximum should be should be 534. Here there is like something is missing. It should be 22. And this one we can change the axis. We can say the smallest one was 168. Let's say 160 e to the 6. Okay, so now it looks a bit nicer. And you can just read if you want to get P90. So let's copy that first before. Okay, again P90, I come here and I find exactly that number, P50, that number, and P10, that number. Okay, and it's consistent, actually gives me that it goes increasing. So let's see, P90 for this particular case is approximately 260 million standard barrels. P50 is approximately, how much will that be? 330, no? Okay, and P10 it's 430 more or less. Yep. There is another, also a formula you can use to find this P90. I forgot the name. Is it called quant something in Excel? Well, there is a way that can read automatically that number for you. If it doesn't appear, what do you have to do here? If it doesn't appear exactly 0.9, like in this case, it jumps from here to here, you can use an interpolation. Okay, you decide what was best, but you just perform an interpolation. Clear? So let's go back a bit to this result, and I ask you, we have one petrophysicist, okay, which is, this is A. He's very conservative. Okay, he said, well, the porosity actually, we can say is between this range and that range. Okay, and now comes the second petrophysicist, and he said he's a bit more, restricted. He says, well, I know exactly the porosity should be in a smaller, more, closer range, like not so wide. How will you expect that will affect this distribution of the n? Now we are speculating, okay? You actually have to do the calculation. But if I have less uncertainty in a parameter, what I will expect is that this will become a bit thinner, okay? Right? It will close I will try to, it won't be so spread, okay? And then you might have also the case where one petrophysicist is maybe too positive, he's too positive, and one is too negative. And in that case, you will see that maybe the distribution shifts a bit to the right, for example. That's like an optimistic distribution, and the other one to the left is like a more negative, less positive distribution. Okay, so don't be when you solve the exercise, don't be scared, if you see that the distribution changes. That's how, it should do. That's what should happen. And that depends, really shows you what is the impact of each, remember, each one of these factors that we have in our Excel sheet are actually defined by okay, by field data that I gathered, by information from experts, so the interpretation, how you interpret the results of the test, okay, of the drilling, the coring, the logging, also plays an important effect on the final distribution that you compute. Yeah, sometimes can be too optimistic, sometimes can be too negative, or sometimes it can be more uncertain. Okay, these are basically the things that can happen. So if you have a shifting in that direction, you see like it's less optimistic. Okay, and the spread, that tells you something about the uncertainty. More or less uncertain. Okay, so I'm going to write the equation for the triangular distribution. Triangle distribution that you will have to use triangle distribution. So P as a function of x. Remember, triangle distribution is defined by three numbers, A, C, and B. Okay. So that's the most frequent value, that's the mode. And the cumulative looks something like that. Sorry. So okay, why does it look different than the other one that we had before? Than this one? It is the way I sum, right? I calculate the cumulative probability. In here I was summing from bottom up, and in the other one I'm summing from top down. So what is the difference? How do I interpret this number here? There is 0% chance, right, that my let's say that this is porosity will be equal to A or less than A, right? And then you have for example, if this is 1, right, this is 0.5, there is 50% chance that my porosity will have this number or less than that. Okay, so be careful. It's the same thing, the same information. The difference is how from which end I start to sum. So be careful on that. Okay, so the equation is so the function for this is so I'm going to define a factor called W that will be between 0 and 1. This is a random number. Okay, that's the CP. So I have a function, I have already W, A, B, C that depends on the three numbers. So for W between 0 and FC, I have that x is equal to A, that's the value of variable, right? X is this axis, in my case porosity, whatever, plus the square root of W times B minus A times C minus A, and for W between 1 and FC, then x will be B minus square root of 1 minus W, B minus A, B minus C. Okay, and function, but we need something else that we are forgetting. What do we need? So, okay, we need fc, right? Fc nobody has defined. Of course, this is a function which is, you know, here you have a slope and here you have another slope, right? So the integral should also be divided in two parts. Okay, you should use one equation for here and one equation for this section. So that's exactly what is happening here. If I choose a number between, that's fc, right? That's a cumulative, sorry, fc. That's a cumulative distribution of c. If I choose a number between fc and 1, then I have to use that slope, right? And if I use a number between fc and 0, then I have to use this slope. Everybody see that? Or you're already falling asleep? Okay, so that's why I have these two fours for these two equations. And just I need to know how much is fc. Okay, for fc simply is fc, which is, you know, the cumulative distribution at c will be just c minus a. You can do the math, divided by b minus a. Okay, you will find in your professional career, if you end up doing uncertainty, you will find all kind of functions to define input variables. The triangle, these are the most common, but you have also normal, you have log normal, you have, you know, a whole library of different functions that you can use. And it becomes the complexity is actually to, you know, to back calculate. When the function becomes complex, the integral also complex, and then you have to back calculate the value from the CP. But that's the only complexity. The rest is exactly the same. Okay, so now let's go to this particular question to say how many iterations are required in Monte Carlo.
Excuse me?
Yes?
I have a question. So this formula is for the triangle distribution.
Yes.
Is there a way to like come up with the formula if it's like a different distribution?
Yeah, you because each formula, if you find on the web, for example, the normal distribution, okay, it usually tells you the PDF probability and tells you the CDF. Okay, so here this gives you actually the number between 0 and 1, right? And then you have to find out what is the x. And that's what I'm saying. In our case, if it's triangle, you can actually make some very simple mathematics and you end up with this expression. Here you have this error function which you probably have to solve some other way. But that's what I'm saying. The complexity is really in the shape of the function. Yes? And you have all kind of different functions, normal, gamma, you name it. But remember, we don't want to use, if you don't have enough information to support that function, why to use it? Okay, unless it's something that people already know because they have done many tests and they say, oh, porosity is always a normal distribution. And that's when you use it. But if you have one point measurement and another point, then you say, I'm going to use something very fancy. What's the point? You don't have any more information to sustain, to prove that that's the best. Not always the most complex is the best. Okay? Clear? That one you will have to create a function, or you can decide how to do it. So you create a VBA function with the triangular distribution, and this will be the random number and the A, B, and C that I provided for, I think this is for exercise. For example, for the recovery factor, you will have to use it because this is a triangle distribution. Okay, so how many iterations do I require in Monte Carlo? So let's say that I have a full population, right? Of, let's say this number is extremely big. Okay, I have a population of infinite, some number very, very high. Let's say 10 to the 7. A very big number. And if I try each one of these points, okay, and each one of these points, remember, is a particular combination of porosity. In our case, this point P is a particular combination of porosity, P, BOP, VRP, what else? Saturation, P, and what else?
Gas gross.
Yeah, net to gross, P. Right? If I were able to sample, or if it was possible to make infinite, a very high number, I will find that my N, right, will look like, probably like that. Okay, very narrow, or particularly narrow, and with a very clean mean. Okay, that will be my mean. Okay, that I say me, that's my mean. As a function of n. In this assumption, I'm assuming that the variables that I compute with Monte Carlo are normally distributed. Okay, they look like a bell-shaped distribution. That might not always be the case. Okay, just be aware of that. But for this, to find the number of iterations, one assumption is that n, if the number of samples, no, you say I have problems, number of samples is infinite, then n will tend to go to a normal distribution. But in reality, I cannot make, because it will take forever. You will be sitting here until you're old, and then we die, all of us, and then my grandchildren make simulation, etc. So we can, due to time, we cannot make all of those runs. We can make only on a small sample, right? We can make, let's say, what we are doing now, n equals 1,000 iterations. When you calculate that distribution, how it will look like? How do you think? First, it will probably be wider, right? We are not sure, but we will probably be wider. And it will probably have another mean. Yes? Okay, not the true one. Only maybe if I am very lucky, it will be exactly on top of this one, right? But this is, so let's see, this is n. So let's see here, this is n with, sorry, I shouldn't call it n. N is the number of samples, okay? Let's put it here, number of samples. N is, this is infinite number of samples. Okay, I reached the true value. And this blue one, discontinuous, is when I have a finite number of samples. Okay, now what I want to make sure is that this distribution, if I define an error, okay, of that distribution, let's say here I define an error that I'm going to call E. I want to be sure that I take enough samples such that I'm moving this distribution such that this, the real value of n, will be inside this error, plus minus, inside that blue distribution. Okay? So that's my main assumption. So let's put that error, okay? Okay, so I'm saying that n bar plus the error, okay, should be greater or equal than this. This is the real mean, and should be also less equal than n minus e. I should bracket by using this error plus and minus. I should be close enough such that I'm containing that part. Okay. Now that error, usually I can do two things. Okay, I can say that error is, I can define it as I have computed with my Monte Carlo the average, right? Or the mean. In this case it's normal, so they are the same. So I can define this error as a percentage of n. Yes or not? I can say 2%. Something arbitrarily, something that I'm satisfied with. I'm going to run so many Monte Carlo simulations such that my interval will be 2% of the mean that I calculate. Okay, in my example will be, I want to have an accuracy of, how much was the mean here? 314 million barrels. So I want to be plus minus, how much is 1% of that? 3 million barrels, right? That's my accuracy. That's how much I want. Okay, I'm not sure if the real mean will be here or not, but I want that if I use plus minus 3, the mean will be in one of these positions, the real mean, after I run 1 million iterations, or 10 to the 7 or 10 to the 8 billion iterations. I want to be sure that the real mean will be someplace here. Okay, if I'm very relaxed, I can say, well, I want to be sure that it's within this range. Okay, and then I will need less and less iterations. Okay, so that comes to the conclusion that the error, I'm going to say, is defined as a percentage. Okay, so I can say usually we use 2% of the average. Of the average. Okay, so that will be 0.02 times the average. But at the same time, I want that this error will, for some reason, okay, that I want that error on my distribution that I calculate for n, okay, I want that error will cover exactly a big percentage of the curve. That will cover 98, 95, or 97% of the curve, that range. Okay, and that's what I call the trust, or the confidence interval. Okay, that's my confidence interval. At the same time, I make that request, that I say, well, I want that this range that I'm getting, it will have a confidence interval. It's something that I define, 98, 96, 97, whatever. We usually use, some places we use 98 and 90 or 97. Okay, some 95, sorry. 98, that means that the bracket should be 3 times the standard deviation, okay, of the mean. Okay, if you want it to be 95, then it's 2 times the standard deviation of the mean. Well, 1.95, I think. Okay, that's another restriction you have. So you put both of them together. You say, well, I need my distribution to be 3. This number should be equal to 0.02, the average. Okay. And to find the standard deviation of the mean, you use the standard deviation of the sample divided by the number of, well, not sigma, but you use s actually, of x, divided by the square root of the number of points you have. Okay, so I substitute that here, sx divided by n 0.02 times n, the average, and then I obtain, clearing n, I obtain that n is equal to 3 times the standard deviation of the sample divided by 0.02 times the average to the power of 2. Okay, so the logic is that if I make a finite number of iterations, okay, I'm going to get a distribution that might not look at all like the distribution I will get if I do 1 million, 1 billion iterations, right? But I can force the distribution I find, this blue distribution, such that if I define an error band small enough, then I can find the number of iterations I need to keep that band very small, okay, very close. And that's what I have done here, okay? And that I do by defining arbitrarily. Here I'm defining that the error should be 2% of the average, but you can be more strict. You can put 1%, you can put 0.05%, okay? So that number you control. And then you also say that this error band has to cover at least some percentage of this normal function, okay? That I call the confidence interval. And that finally, that's what tells you the number of iterations you have to do with Monte Carlo, okay? And if you notice you need the standard deviation and you need the average. So you need to run first, assume a number of iterations, run, you find these two numbers, you run it again, and a higher number of iterations, and that's how you start converging on the number of iterations, okay? We will, that was, okay, so we have 5 minutes left. Any question? Or many questions, or no? Okay, so just to be clear. So if you want to find the number of iterations, you come here and you calculate the average, right? Average of this column. Okay, that gives you 312 million barrels. And I want to say, well, the error has to be plus minus 3 million barrels from that number, okay, or 2%. Then I calculate the standard deviation of the sample, and it's this standard deviation P. Okay, so this will be the average, and this will be the standard deviation. Okay, and then to calculate n, I just have to say this was open parenthesis 3 times the standard deviation divided by 0.02 times the average. Okay, and that all of that to the power of 2. Okay, and here we have an error. Oh yeah, sorry, this should be, I should have a bracket here. Okay, 1127. But after you increase the number of iterations, you have to redo the same calculation and see if the number increase or decrease. Okay? Because you will only know after you computed the distribution, the blue distribution. Okay? You don't know, if you don't have the blue distribution, you cannot do any estimation. Okay? So let's, so now you have all the tools you need to solve the exercise. So let's say today is the 12th. So we are going to put the delivery date, let's say for the 28th, okay, of February. And it will be published. Remember, the delivery is in Inspera, so you will have to deliver through there and in groups. And we will try to do it as soon as possible in Inspera to make it available. Okay, so let's put here on the notes. So that's exercise set 1, delivery date It's the 28th of February 2018, and let's put 12 at night. Okay, so let's see 23.59 okay. Trondheim time. Okay. So to summarize, today we solved the exercise. I showed you some tricks in Excel. Those of you who already knew it, that's fine. Those of you not, I hope you at least got a feeling how to start with the exercise. And the distribution we obtained, exactly what we expected, this normal distribution. I explained how you deal actually with that distribution. By itself doesn't tell you much, but you have to calculate this P10, 50, and 90, and those are usually the numbers we use in the PDO. Okay? And yeah, and then the number of iterations you need for this Monte Carlo simulation. So see you tomorrow. Thank you for coming.